Sorry. The key idea about logical relations is to associate a relation or a predicate, a relation with a type in a type programming language, so with a type, and to derive, we're going to use it to derive, in our case, we're going to look at derived properties of programs. So what is going to happen in various type theories and so on? So I'm going to explain all of this, but this is a very, very high level idea. So the informal motivation is that whenever you write a typed programming language, when you assign a type to a program, you're, so to say, proving a theorem about it, because you're saying that it has some behavioral characteristics that are induced by its type, and the theory of logical relations is the way in which you make that precise. That's it. So this is what I'm going to talk about, and this is going to be used. These techniques are used in a number of applications, and in fact, there are many ways to motivate it because, like many good ideas, they have multiple applications in different domains. I'm going to focus on the programming languages domain because I feel myself to be sort of setting up for work that Amal Ahmed and Nick Benton and some others are going to be talking about later. So I'm sort of providing the foundations for that. So what I'm going to do is everything is built around the idea of type, which Frank has started to broach with you this morning via the propositions as types correspondence, and I'm going to build on that. And what I'm going to do, and I don't know whether I'll be able to get through everything that I want to get through, but I'll try, is I want to go through a couple of sort of case studies that illustrate central ideas in the theory, in the field. That's what I want to do, to derive for you the things. So I want to study a couple of formalisms. One I want is a little functional programming language, or at least that's what I'm going to construe it. So we'll call it Gödel's T as thought of as a programming language, okay, which is a simple formalism which I'm going to describe momentarily, which deals with the idea of higher order functions over a base type of natural numbers. Okay, very simple, like basic starting point. Lots of things can be based on this, and I'm going to give you an example about using logical relations. Then I would like to study for a bit Girard's system F, again construed as a programming language, and I'm particularly concerned here with explaining the idea of polymorphism or the idea of parametricity. You can say the theory of logical relations. Oh, I'm sorry, did I do something wrong? What? Say? I can barely read. You can barely read, all right. Okay, I will, that may be, I'll do my best. Is it because it's not bold enough, or what? Like the color thing, or what? Okay, I'll just write larger. I'll try to write larger. Okay, so which is what I was saying is the theory of logical relations applied to polymorphic types is also known as the theory of parametricity. So we'll talk about that. And then I would like to talk about the LF language, which stands for logical framework. And what I want to discuss here is the basic theory of dependent types. Okay? And if we get through all of this, that will be great. I'm quite confident I will get this far, and I'm not quite sure whether I have enough time to develop these ideas in detail or not. We'll see how that goes. But these are some core ingredients. So that's the sort of plan about how I'm going to organize the material. So what I want to do, my strategy here for presenting it is, I, so to say, would like to invent the subject with you. Okay, that's what I'm hoping to do. I'm like trying to show you how you could, it's not necessarily historically accurate, I'm not trying to be. I'm just trying to show you a particular way to think about it that I hope will help you understand what the inner game is, like what the ideas are that lead to this particular technique. Okay, so that's my plan. So to start out, I want to look at this very simple language called Gödel's T. Okay, which were written here. And Frank has very helpfully gotten us, you could say, halfway there, and I'm going to push us in a direction that's a little odd with respect to his lectures, but everything will make sense in the end. There's just a question of meshing the timing of what we say when. So let me just jump right in. So what I'm going to do is I'm going to look at a formalism where my types look like this. I'm going to have a couple of different things. I'm going to leave a little space here, but I'm going to have a base type, which I'll write omega for the natural numbers, and I'm going to have function spaces. So, which in Frank's this morning was talking about proof theoretically as a function type. So the thing that's a little odd is I'm going to take a type, this is going to be a type of natural numbers. And at the moment I'm not going to need it, but a little later I'm going to need for the sake of exposition, as for the reasons of making certain points, I'm going to need a base type of, you can think of this as Booleans, but it's not even Booleans, it's just a couple of observables, which I'll come back to that a little bit later. For right now, in fact, for this lecture, let's not worry too much about that. It's a technical issue. Okay, so the point is I want to have this as my type structure. So I want to be able to talk about, for example, functions on the natural numbers. So that would be functions of type omega arrow omega, functions that take a natural number and yield a natural number, or functionals on such natural numbers, and so on. In other words, I would like to be able to talk about rich type structures built up from just functions on the natural numbers. That's the whole idea. So this was a formalism that was originally introduced by Gödel, and I think in the 1950s, if I remember correctly, whose purposes are not going to be apparent here because I'm just stealing the formalism for other purposes. I'm not going to explain here why Gödel introduced this, okay? But in any case, that was the thing. So we're going to have a bunch of terms that we use for this, and these are the ones primarily for this part of the language, is what Frank was telling you this morning. So we have variables, okay, and we have lambda abstractions, which I think he wrote like that, or pretty close, and we have applications. Let's write M1 applied to M2. So that's the part I think that we just got through seeing in the last lecture. So this is a sort of functional apparatus that we were talking about before. And now in addition, I'm going to have some things pertaining to the natural numbers, and it ends up being convenient to just present them in a unary form, and that has to do with some other points I wish to make. Let's just bear with me why I choose this particular example. So we're going to have a way of writing down 0. We're going to have a way of writing down the successor of any number, and then we're going to have a particular thing called the recursor. So that's the distinctive feature about Gödel's T, and I'll explain the operational meaning of this momentarily, but before I do that, let me just give it informally. Here's what the syntax is going to be, and we'll write it down. There are different variations on this, and we can play around with lots of versions, but here's the idea. So you can think of this, if you've never seen anything like it before, it's sort of like a for loop, if you think of it in terms of imperative programming, or it's better known as a recursor or iterator in some form, which allows me to count up to a particular number. So the whole idea is that what we're doing here is you can think of this as something like, if you know Camel or standard ML, it amounts to defining a function that says, let's call that function, for the sake of reminding you, let's call it R, standing for the recursor maybe. And it amounts to saying, well, what it does on 0 is it gives me M0, and what it does on the successor, okay, and then there's a way of writing this, successor of, let's call that x, that's supposed to be a variable. So then there's a way of, however we write this, the point is these are bound variables that occur within here. So one way to write this would be something like, well, let x be, that's x, so let y be the recursor, make the recursive call on x, and then run M1. Okay, so that's the intuition. So we can put this here as in quotes if you've seen something like ML before. So you're doing pattern matching. You're taking M is going to be a number, and it's either 0 successor. If it's 0, then the answer is M0. If it's successor of something, that's X, then call yourself recursively on the predecessor, and then compute your answer as a function of both the predecessor and the result of the recursive call. That's the setup. Okay, so that's what that's supposed to be, and that's Gödel's T. Yes? Okay, go ahead, sorry. I didn't hear. Yeah, that's the idea. So there's two bound variables here. So like lambda has one bound variable. If I wanted to be highly regular about the syntax, I might write lambda and it has a and x dot m. The point being the x is bound within m. That would be like a particularly regular way of writing the syntax that would be similar to what I'm doing here. Okay. Maybe I should mention, by the way, I should have said this in the beginning. As a reference point, let me just throw it in here. You might look at one thing you might look at, especially since it'll be more or less notationally consistent with what I'm doing here, is a draft book I have online called Practical Foundations for Programming Languages. It's on my webpage. And not everything I say here is in there, but a lot of what I say is in there, and a lot of other things too. So you might have a look at that. Yes?
Clarify, why is not like a label? It's the result of the recursive call.
It's the result of the recursive call. That's what is happening here. I'm calling R recursively on X, and so to say, baked into R is M0 and M1. I could make them parameters of the recursor if I wanted to make it, if you like.
What is M?
Say.
M?
Oh, that's supposed to be, well, let me write down the static semantic. That's supposed to be, oh, I see, I'm sorry. Yes, thank you very much. This would be run R on M. I forgot to write that down. So define R this way and run R on M. That's what that does mean. Thank you for pointing that out. Yeah, that's right. That's exactly right. Okay, yes, good. Yep, thank you. Okay, good. So then we have, just to define this language, we have a statics and a dynamics, right? And so the statics, and this is again what Frank had broached this morning. So for the statics of the language, we're going to associate a typing judgment exactly of the kind that Frank was using. And I think this is pretty much his notation, where this is called gamma, which usually written gamma, which is the typing hypothesis. So it says assume that these variables xi have the type ai given to them, and under those assumptions deduce that the term m, which is drawn from this language here, has the type a, which is drawn from the language given there. So this is the typing rules, if you will, or the static semantics of the language. And this is much the same as what Frank used. For my purposes this morning, I'm not going to make any supposition about ordering here. I'm going to say that everything can be permuted quite freely. So I will write, for example, I'm not sure whether Frank will get to a situation where we care about order, but sometimes we do. But in this case, we won't. So I'm just saying if you assume, that a variable has type A, then of course it has type A, so that's a simple thing. Then the rules for the lambdas for the functional part of the language are what Frank gave, modulo possibly some minor notational difference. So we'll call that AROB. And how do you type check a function? You assume that the parameter has the type you gave it, and you check that the body has the type of the range. So this is the domain, and this is the codomain or range, however you like to say it. Okay? And similarly, I think Frank gave a rule that says if I have a function m as a applies a or b, from a to b, and I have an argument of type a, then I can apply it, and it will be of type b. And in fact, the origin of this, as Frank was beginning to explain, is this is the so-called introduction rule. So this would be, I don't know where to write it, we'll write I here. And this would be the elimination rule for the function type, how to use a value of function type and how to create a value of function type. So that's a pattern that we'll see recurring whenever we're talking about type theory. And then Frank gave a dynamics as well. He started to talk about beta reduction, and I'm going to define here a restricted form of dynamics, and this is where it becomes sort of more of a programming language. I'm going to define two judgments: what it is to be a value and what it is to take a step. So this is these things together constitute a transition system, what is called a transition system. The states are going to be closed terms, so these will be unclosed. So this is where I'm doing something a little more PL-ish rather than proof theoretic. There are many variations, as I've said, on all of these things, so this is a particular way of looking at things. So I'm going to define a transition system, which is going to be my execution model, my model of computation. And as Frank had mentioned this morning, the way in which we get that is the inversion principle, where we think of the elimination rule as being undoing or reversing or inverting, if you will, the introduction rule. So we get a primitive form of rule here. One of the rules for transition looks like this. It says if we have a lambda and we apply it, so this is of the form elimination applied to an introduction, right? This is an introduction form, and this together is an elimination form. And now we're going to say, so to say, they cancel. So in some sense, what I do is I plug in n for x in M. And the idea being that if I take this rule and run it backward, the content of having a lambda abstraction, a function of type A or B, is that I have an open term of type B with a variable of type A, and then by substitution, I can plug in that particular argument of type A, and that's my notion of reduction. So this is a simplification, and this Frank, I think, called beta reduction. Classically, this is called beta reduction. Okay, and so we might call it that. I'm going to have more to say about the dynamics in a minute, but that's certainly one notion. Okay, and then similarly, we have a pattern of introduction and elimination for the natural numbers. So what we'll say is that 0 is a natural number, and we will say that if m is a natural number, then the successor is. You are not surprised by that. And then how do we give a typing rule for the recursor? So if this made sense to you, then it will be no problem to derive what the typing rule for the recursor is, because it's a kind of conditional branch, isn't it? So what it does is it says I have a number. This is what the question raised, which I forgot and neglected when I was giving my explanation. It says if I have a number, and I know what to do when the number is 0, so that's why I called it m naught. And whatever I do with the number, I can do whatever I like. So it's going to be some type A. I don't care to specify what the type of A is. And then I have to say, well, if it's not 0, then I'm going to give you an answer which is also going to be of type A. And the reason is because I want to know that you don't know a priori whether m is going to come out to be 0 or non-zero. So your outcome, if you're going to give it a type, has to be the same regardless. So that's why we're going to have A here and A here, that's for sure. And then in addition, when I'm type checking as I suggested here, when I'm type checking in the successor case, I get two additional assumptions. One is that the predecessor is, of course, a natural number, and y is the result of the recursive call, right? So y is of type A, the recursive call being of type A. And so you'll notice that there's a pattern here that will come up later, which is that we have A arrow A leading to A. Okay, so you're going to see this pattern a little bit later on, and you'll remember this, just remember this little pattern. And when I talk about system F, we will return to that pattern. So I'm just reminding you that, because if we think of these two things as inputs, then the input is of type A, and the input is of type, well, A arrow A, not quite, it's omega arrow A, but let's say we neglect that part momentarily, just to call attention to this particular point. So we have something that transforms A's into A's, and those two things together give me an A. Okay, we'll come back to that later. Right now it's just a little remark about the way the notation works. Okay, so good. So now what I want to do is say something about the dynamics of this thing, and the way I do that is I'm specifying once again, these are both the intro rules, and this is the elimination rule. So we're going to have the same pattern that the elimination inverts the intro. So the idea will be if I'm running the recursor on 0, then what do I do? Well, remember what the intended meaning is. The intended meaning is check whether this is 0. If it is, then the answer is m naught, so we do that. And if it's not, so it gets a little tedious writing this out, sorry about that. But I just have to do it once basically. So here's what I'm going to do now. So what do? Well, it says if it's non-zero, we know that it's non-zero, then we are going to execute M1, but with x being the predecessor, which in this case will be m, and y being the result of the recursive call. So I do a substitution. I'll write it as a simultaneous substitution. So it's m together with something, with x and y, in M1. So I'm going to run M1, binding x to m, and what do I bind y to? The recursive call, the very same thing on m. Okay, so I say rec m, and now I'm just transcribing, I'm not writing anything new. The very same guy being applied to m now, okay, for the recursive call. Okay, so that's the setup. So that's how we explain this. So this is the idea of recursion on a natural number. Okay, so that's the point. So the reason it's analogous roughly to a for loop is that unlike a sort of while loop in a conventional programming language, whose termination condition is could be rather subtle, here the termination condition is not rather subtle because I'm basically counting, right? So I'm giving you something to count up to, and I count up to that. That's why it's a little bit analogous to a for loop. So that's going to come out momentarily when I talk about the relational interpretation of this type theory, because that will be, we'll get to that in a moment. Okay, so these are the basic ideas of the dynamics. That is, these are the instruction steps. So you can think of this, I'm defining an abstract machine. When I define a transition system, that's another word for abstract machine, if you like, okay, because it tells me, given a state of the machine, what is the next state, and when am I done? You could think of it like that. So I'm defining a computing device. And this is my instruction set, right? That's what I'm doing. So the instruction set here is a relatively high-level thing, unlike to machines you're maybe used to. But it nevertheless has the same characteristics. I have a very definite idea of the state of the machine and what it means to execute, take a step of execution on the state. Now, there's something more that we need, and the thing we need is that this is well and good. It tells us that if I have a lambda in front of me and I apply it to an argument, I can reduce it. But we also need some additional rules, and also here, this tells us what to do if I have a 0 in front of me or if I have a successor in front of me, with right where me in this case is the recursor, then I know what to do. But then we also need some rules that tell us how to figure out which lambda the function is. So if I take in general, if I have any term mn and I want to execute it, well, the only possible execution that I've given so far is one in which this is exactly a lambda. But maybe it's not a lambda. Maybe it's an application applied to something else. It's a nested application. So obviously the way in which we're going to deal with this, is there an eraser somewhere? Yeah. The way we're going to deal with this is we're going to specify execution in the following manner. What we're going to do is we're going to say, well, another notion of execution is written like this, that says if you have an application and m is not a lambda, where it will come out that if this is possible, this can't be a lambda. We'll see that in a minute. But the idea will be that if I can take a step of execution on just the function position, do so, and the state of the machine is I'm still applying this guy to n, but now I've made progress on the function position. So this is one rule that I'm going to give. And then another rule I will give is directly analogous, which says for the recursor, because the poor recursor, the instruction tells us what to do once we've figured out, okay, whether something is 0 successor. But in order to get to such a situation, then I need to be able to make progress on what is called the principal argument, the argument of the recursor that is a number, to figure out what number is it, okay? So these are some basic closure conditions that are going on here, okay, for execution of a program. At a very high level of analogy, if you were to think of, the operational semantics of like an assembly language program, then this kind of a rule would correspond to if I have a sequence of instructions, then what I do is I execute the first instruction and then do the rest. So there's something similar flavor of what is going on here. Okay, so now there are some branch points here. Oh, sorry, yes, please.
So we have a small step called by name semantics.
Yeah, so that's right. So I was just about to introduce some terminology. So thanks. You're one step ahead of me, one small step ahead of me, maybe. And it's just my very next sentence. Okay, so here's what sorry. I didn't hear that. All right. Anyway, so where was I? I lost my thread. Oh, okay. So yes. So this is called this thing here is called call by name. All right, CBN, as I've written it down here. And I'm going to use that because there are a lot of choices now. Okay, and there are ways of making these choices not arbitrary. And in fact, they tie in with what this idea of what is called focusing, which Frank will come back to a little bit later. But as a matter of staging of ideas and concepts, I can't really do that. So right now, what I will say is there are some seemingly arbitrary choices here, okay, that whose justification and understanding will emerge later, okay? So right now I'll just say there's some arbitrary choices. So one arbitrary choice is using what is called the call by name reduction strategy, which is, notice that I don't do anything with the argument prior to plugging it in. I just plug it in unevaluated form, okay? What is the alternative? So an alternative, and there are some other things as well coming up. And alternatives, I'll just mention. So one is called call by value. I'm sure you know this, in which I have an additional rule. Oh, and I haven't actually, there's something else I forgot to do, which is write down what are the values, okay? So what are the values? Let me just write that down momentarily. So what are the values? 0 is a value. Success, yes, we're gonna, that's why I didn't write it down. We're gonna have a, let me write a question mark here. I'll come back to that in a minute. And a lambda is a value. My point being, if those are going to be the finished states of execution, that's what I'm going to write. The question mark I'll come back to in a minute. So call by value says, well, if you know what the function is, it's a value. So actually it's a lambda. We will know for various reasons that we'll get to in a moment, but let's leave that. And the argument can take a step. Then I can have a rule that says, in addition to the ones I've had here, I can say you can go from mn to mn prime. And then you restrict, so the call by value is two parts. You do this, and then you restrict the beta rule so that n has to be a value. So we say lambda x m applied to n. You have the exact same rule of reduction, but then you demand that n be a value. So these two work in tandem because you see, if I demand that n be a value, then I need a way of getting it to be a value by executing it. So that's why this restriction sort of motivates that rule. Okay, that's the way of thinking about it. And that would be, those two things together would be call by value. I'm not going to consider that. Another thing which is going to emerge also in the context of focusing is the idea of eager versus lazy. So the nice thing about Gödel's T here is that it's a bit of like, it's the E. coli of programming languages in a way. It's a very useful object of study. Okay, there's like lots of issues can be embedded in this very little formalism. So that's why I chose it for starting this. So what do I mean by eager versus lazy? Well, it has to do with this rule. Okay, so when is a successor a value? So under the lazy interpretation, lazy successor, we just say this is a value. So this is, we'll call that the lazy interpretation, regardless of whether m is or not. So the idea is you're just lazy about it. You just say, look, after all, the only thing the recursor cares about is the outermost form. So why bother evaluating this guy until you absolutely have to? Maybe, you know, just be lazy. If you plug in for x and y in here, maybe M1 couldn't care and doesn't even bother to use x or y possibly. Maybe it's a constant, in which case, you know, there's no point in evaluating m. Hey, you know, if I don't have to do it, don't bother. We'll do it when I have to. So that would be the premise, okay, of how you do that. And that's the notion of lazy evaluation. The alternative, and then we would be done with that. The alternative is the eager strategy, which is to say, well, no. The successor of m is a value only if m is a value. And then in compensation, to sort of make that a usable principle, then I need a reduction or a rule of the dynamics that says we can make a transition from m to m prime, okay, like this. So these two things together constitute the eager interpretation, okay, so that we can write it like that. So those are all on the table and all in play. And in fact, yeah.
Does it really make sense in practice to combine, does it really make sense in practice to combine, for example, the call by value semantics with the lazy semantics?
Yes.
Okay, I thought they were usually paired. Call by name with.
Yeah, I don't want to comment on usually because then it gets me a long, far field. But the only thing I would like to say is that I hope it's clear that the rules I'm giving are separable because S of m is not a use of application. In other words, this, if you wanted to really be official about it, I have apply mn, right? And then in order to be really emphatic, I have a separate thing called successor of m, and those are just two different, operators in my language, and I can treat them quite independently of one another. Now, sometimes people work it out so that the successor is the application of something, and then you get into, I think it's better just to not go there, right? So let's just say, in the way I've set it up, I have a freedom of choice here. Okay, and they're not coupled. Okay?
Either way. Functions have successors either way, do they?
Say again, please.
A function, you can apply the successor thing to all values, so you can apply it to functions? No, you can't.
I'm not sure if I understood the question, but the idea is that the successor is not itself a function, it's a way of forming expressions. Okay, yeah, okay. In other words, maybe I didn't understand the question. I want to distinguish sort of, successor of m from the function, the successor function, which is lambda x successor of x applied to m. Those are two different things. That's another way of saying, did that answer your question? Okay, should we try again?
I was just wondering whether S of m, where m is a function, is well formed.
At this, it's not going to be well typed. Okay, you can write it down as a hunk of syntax, and it'll just be ill typed. That is the idea. The reason being, I would have to prove this to you, but one can, that to form a well-typed successor requires that m be a number, and a lambda as a function is not a number. Now, in order to know that, you have to know something that this type can never be equal to that type, and that's the case because it's just a freely generated words over they're little trees, and those trees yeah. Anyway, it's obvious if you take that as your starting point. Yes.
So going back to the form of the recursor, I'm wondering why we do abstraction separately for the recursor instead of just saying rec m, m0, m1, and m1 should have the type.
Yeah, you can do that. So there's sort of, it's very difficult for me to justify everything.
Okay, so there's no solid reason.
I don't want to mix up the meaning of natural numbers with the meaning of functions. I prefer to take them separately, okay? So that's the way I would say it, okay? So it's better if I not try to go far afield on that. Okay, so yes. So I'm trying to illustrate some, let's say, experience says this is a good way to go. That's right now, that's the best I can say.
In eager semantics,
Yeah.
would you want to restrict the evaluation of recursors?
Oh, I do. I'm sorry. Yes, I do. Thank you very much. Let's see. No, I don't need to do that. So I know what you're getting at, and that's a very good point. And so the question is a very, very good question. If you're going to do substitution, like one way to interpret the eagerness is to say variables always stand for values. So that when I use call by value, what I'm doing here is only ever plugging in a value for a variable. Now, so a natural thing to do then would be to say, if I'm going to use call by value, think of variables as ranging only over values rather than over general computations. And then I have an issue here because I'm substituting something which is quite definitely not a value. It still has to compute, and I'm substituting in for a variable. So in that case, if I wanted to maintain that point of view, then what I would do is introduce some sequencing operation, a kind of a let binding, really of the kind that I described here, to bind the result of the recursive call to a variable and then plug it in. So that's why I don't want to go, I don't want to go there because it complicates the formalism. So the reason I stuck with call by name is for pedagogical purposes. Okay. Yeah, it's a perfectly beautiful, appropriate comment. Thanks for that. That's very good. Okay. Did everyone understand that? It's an issue of the maps in some sense, right? So what's happening is if I'm going to do these things call by value, then the intuition is a free term thought of as a map. The domain should range only over values. That would be the intuition. And then one has to then build up that. And you can do it, but it will obscure what I really want to get to here. So that's why I'm choosing my path, okay, carefully, I hope. At least I intended to. Okay, good? All right. So this is the setup of our language anyway. So I'm not going to, what I'm going to do here is I'm going to deal with the lazy successor, and I'm not going to deal with call by value, I'm going to deal with call by name. This will make things work smoothly for me. Okay, so now what I really wanted to get to in this lecture was to help you, so to say, invent the idea of logical relations by asking us to prove what might seem like an obvious theorem, and maybe it is an obvious theorem, I don't know, which I'm going to state, which is what is called the termination theorem. Now you might ask, why did I pick this? And the reason I picked this is purely because my real point here is to show you the theory of logical relation, so I'm contriving a question for which that's the answer. Okay, so that's what's going on here. There's lots of things one could say about Gödel's T, and I'm choosing to take one thing in order for illustrative purposes, just so you know. Okay, so termination theorem. So what I want to say is, and here, I'm going to phrase it in a very particular way, in a way. So what I want to do is this. I want to prove a theorem that says it's in some sense the weakest thing. If M is of type omega, then M terminates. Oh, M terminates. This means, sorry, M reduces to, let's call it V just to be emphatic, such that V is a value. Okay, so this is what I want to do. And so this is the main point of this lecture. I hope I will manage. We'll see what happens. I want to get through or show you the outlines of the proof of the termination theorem. So that's my goal. So, yes? Could you say? I wasn't able to hear you.
The star on the
Star.
You really need it?
Here?
Yes.
So that means, that means 0 more steps, right? Iterate, oh yeah, I could have defined that, so I didn't define that, which I have to find a place to put it. I'll put it here. So we can say everything reduces to itself in multiple steps, and then head expansion. If M goes to here, and this goes in multiple steps to N, then so does N. By the star, really. That's what I mean by star. Was that your question? Okay. Yeah. So this is what okay. Anyway, these things are, right, thank you for pointing those out. It'll be easy for me to overlook them. Okay, so good. And then defined in terms of that is this termination, right? This idea that M terminates. So embedded in this, the way in which I've stated this, is that I'm embedding the idea, and this is that what we say is we observe termination only at base type. At type omega only, or if I have this type 2, which I'll come back to, it would also be there. Okay, oops, I'm going to put this in quotes. So in other words, the theorem I'm writing, and there's a reason for this, doesn't want to say anything about functions, and this has to do with positivity and negativity. Here's the rough idea. What I want to do is I want to think of a function. In this setup, I want to think of a function purely as a black box. Okay? It's something that I can apply, give it an argument, and it will emit an answer. You can think of it as a foreign function, in a sense, for computer science lingo, that it's just something that obeys the call and return sequence. I don't know what it is internally. So I'm not saying anything about what happens at function type directly. I'm only interested in the things that I can observe, like things which are of type omega. And this is a distinction between a positive and a negative type, which is what is going to come up in Frank's lectures, probably a couple of lectures from now, if I remember his outline. So we'll get to that in a minute. So that's the one thing I want to do here. Another reason why well, okay, let's go with this. Okay, so the question now is how would we think about doing a proof of this termination theorem? Like how would we go about doing this? And so here's where I want to get to the idea, okay? Here's where I want to bring out the main idea, okay, of logical relations. So naively, the only possible thing you can do, right, it's a simple implication, right? So the only possible thing you can do, okay, is to say something about, look at all the typing rules. So the only thing to do, presumably, is analyze or proceed by induction the static semantics. So we're going to analyze the statics, right? We're going to look at what happens, okay, when I have a well-typed term, that's what this means, of type omega. And you're going to see immediately that we're going to get into some trouble, right? It's obviously, the theorem is not going to be, we're not going to be able to prove the theorem in the form stated. It's going to be a corollary of something stronger. And that's actually, that's really all I'm trying to do here. Okay, so but if you start doing this, and depending on where you start, you sort of think, okay, we're doing pretty well. So an example might be, I have a rule that says 0 is type omega, and we're in good shape because 0 is a value, and it evaluates to itself in 0 steps. So that is, it terminates. Okay, so we're good with that. And if we took the next rule, let's say we happen to pick this as our next typing rule, and I'm suppressing the hypotheses, and that in order to make my point. So what we'll do is we'll say, well, what do we do about this? Well, we know, well, it depends. Are we using an eager or lazy interpretation? Let's say we're using the lazy one, which is written here. Then this is a value already, regardless of what m is, and therefore it terminates, and so we're in good shape. But in fact, even if we were using the eager interpretation, so this is the lazy, but if we were using the eager interpretation, we would be okay anyway, because sort of inductively we would say m terminates, which means m eventually evaluates to a value. And then by a kind of pasting lemma, you would be able to show that the successor under the eager interpretation goes to that value, and this is a value, and so it terminates. So in either case, we're in good shape, whether it was lazy or eager, we're in good shape. So that part seems reasonably good. Okay, so that's fine. Of course, we're immediately in trouble if we try to look at variables, because the theorem doesn't say anything about variables. So we don't know what to do. If we're analyzing the statics, so we can say, well, all right, the theorem is only about closed terms, so forget it. We don't need to consider that case, right? This thing is irrelevant because the theorem is about closed terms. So this should really be sort of, under no assumptions, m is type omega. So you say, okay, that's an irrelevant case. It doesn't matter, can't arise. Okay, that looks pretty good then. So let's do some other examples, and we'll keep going. Well, one would be, and this is where we start to get into trouble. Well, suppose I have mn, and then just in order to, we're just exploring how would we prove the theorem directly. So mn is type omega. And if an application is type omega, if you look at the rules which I've inconveniently obscured, you can prove there's only one way to apply a typing rule for an application. So it has got to be that m is type A arrow omega, and n is of type A. That's the only possible way, because there's only one typing rule for an application, and it demands that there be a so-called mediating type. So now we're in trouble, really, because what do we want to do? We want to show that m applied to n terminates. This is what we're hoping to do. So first of all, we're in trouble because unlike this case, the induction hypothesis, there's no induction hypothesis available to us. Why? Because the type A is arbitrary, so this need not be omega. And even if it were omega, this isn't. Okay? And so we're stuck at this point, okay? Because we have no IHs to work with, and therefore you can't hope to get anywhere with trying to prove that an arbitrary application terminates without knowing something about the function in the argument. So we have some trouble. So the first thing you do is you say, well, okay, maybe this idea of only observing termination at some type A, at type omega was a bad idea. Let's strengthen it. Let's just change the theorem and say everything of every type terminates with some value, and I don't care what that value is. Okay? So that we'll get the intended result as a consequence of that. Okay, so then we'll have some induction available to us. So we will know by the first induction hypothesis that m terminates, and we will know by the second induction hypothesis that n terminates. Okay? If we strengthen the theorem. Okay, so we strengthen the theorem, and now we have at least a little bit of induction here. And now you might say, okay, so let's see, now what? Okay, what do we do from here? Can we conclude, like, what can we get out of this? Okay, where can we go from knowing that the function terminates and the argument terminates? Well, it's not going, if you think about it for a few minutes, it's obviously not going to, we're not going to get very far just from that information alone. Because remember, if I say that a function terminates, that just means this expression, which has a function type, eventually evaluates to a value. And I can show, which I didn't prove here, but you can easily show, that value would have to be a lambda, that the only possible value, if you look at the inductive definition of values, which are here, those are here, the only possible value that also has a function type would be a lambda. Okay, that's the only possibility. So we can get from that, so we can, what can we do? Since m terminates, what we really know we'd be able to get out of this is that there's some lambda, let's maybe write it like that, to which m evaluates, because the only possible value for something of function type is a lambda, so we could do that. We can show that. And we know that n terminates, although that seems not germane at all, because we're using call by name, and we don't evaluate the argument, at least not at the point where we do the application. So if you look at the rule for, which is again obscured, but the rule for the closure rule here for application, I can say, well, it follows then that m applied to n can reduce to here, applied to n, because the rule says if you have an application and you can make progress on the function, then you can make progress on the application. So that's what I've done here. So that's a straightforward thing. Oh, and you know what? This is an instruction. So this can get us here, to n for x m prime. So I'm just, as I say, I'm trying to invent the proof with you. So what I'm doing now is I'm just writing down everything I can think of based on what I know. Okay? So I'm just writing down a few things that I know, given the situation that I'm in. So I get that far, and this is where we start to worry. Okay? And there's other places, but this is one spot where we start to worry. So what's happening is, when I run the program, it's not merely, and of course this is obvious, but I want to show you how it works in the formalism. So it's not merely the fact that m itself terminates that is relevant. The termination of the application depends also on what happens to the result of plugging in the argument into m prime, because this now presumably can continue, right, in some form. And for all we know, based on what we have on the table right now, this could go on forever and the theorem would be false. Because nothing we have on the table, this is much too weak. It's not telling us enough about the behavior of the body of the function when the argument is plugged in. Moreover, look at what m prime could be. Well, m prime could itself be like apply x to some other term p. So in other words, the body is doing experiments on the argument. So I'm going to need to know something about that argument, because not only is it going to evaluate the argument by virtue of being in the function position of an application, but moreover, once it is evaluated, that's going to reduce. And so we're going to find ourselves needing a fairly deep invariant, okay, about the behavior of our terms. So to see where that comes from, let's look at the next point in which we fail in our proof attempt. So let's set that aside and try to gain some other information that may be helpful to us in finding a real proof. Okay. So here's another case to consider. So we're going through all the typing rules. So I have AM of type A arrow B, and the hypothesis is XA proves MB, just to remind you. So in other words, we're in the situation where we're provisionally strengthening the theorem to work for any type A, but we're still looking at closed terms. Okay, so if I have a closed term and the type in question happens to be a function type, then the premise of the rule, which is the one I wrote earlier, is we now have a term with a free variable. So now we're no longer, and these two remarks I made go together, so we're no longer closed, so to speak. If you think of this as trying to imply the inductive hypothesis, you're screwed here because you now have an open term. So what do you want to say about open terms? That's the question. So in other words, to apply induction at all, we have to strengthen the theorem further to say something about open terms. And now these two things go together, and this is where I'm heading to. So there's no IH here. On the other hand, you might think, it doesn't matter. It doesn't matter, it doesn't matter, because lambda x am is a value. So we're out of trouble, because all I have to prove is that something of this type terminates, and if it is a value, it does terminate. So it terminates, right? Because it terminates with itself. Oh, so that's good. So maybe I don't need to consider open terms. Okay, so that's where we are right now. So now there's some more stuff. There's a few more rules to go, and another one is the recursor. Okay. But I don't even need to get that far. We haven't considered that yet. I think that's the only rule. Yeah, I think I've now at least put on the board every rule. So we have to consider this too, but I've already got myself in enough trouble. So here I think it's no problem. So what I find myself facing is that I need a stronger induction hypothesis, okay, in order to, than just termination, in order to prove the theorem that I want. Okay, so I'm just checking my time. I have until 10 minutes of, is that right? Someone says? 10 minutes of? 12. Well, I don't want to do that, but okay, I just want to like try to pace myself. So, okay, good. Okay, so now but here already, so it looks pretty good. I did elide this case. Let's just say defer this right now because I want to focus on what we've already done. We'll defer that case. But it looks like, modulo this case, which I haven't discussed yet, it looks like I can pretty much get the theorem to go through, except I've got some funny business going on here, okay? And the funny business has to do with the fact that knowing merely that the things terminate isn't enough of a condition. Okay, so now here is the next idea, okay? So the next idea is I want to prove a stronger result than just termination. Okay, and what I'm going to do, and this is, at this point, is a eureka step. Okay, so what I'm going to do is I'm going to tell you, we're going to prove a stronger property which will be called reducibility. And I'll write it like this. Okay, and I'm going, so here's the intuition. So the intuition is the induction hypothesis of merely knowing the termination of the two of M and N. The sketch here was that's not enough to get our proof to go through. So I'm going to need something stronger. We'll call that property reducibility. It's chosen, the word is a classical word that was introduced by, I'm not sure, Girard or Tate or someone like that, quite a number of years ago. It's meant to, at least for my purposes, it's meant to be vague because, in fact, the notion of reducibility is chosen for the purposes of whatever proof you're doing. Okay? It's true. But there are some conditions on what those should be. This is where I'm trying to get across to you how this works. So don't mind so much that the word reducibility doesn't mean very much. There's a confusing term. Tate called it computability, which is a little unfortunate because he didn't mean like Turing computable like normally people say. He meant it as a term of art. Like it's a particular term that shouldn't be given too much a priori meaning. Okay, so I'll use reducibility, a similar thing. Okay, so don't like imagine that means anything very much beyond whatever it is I need to make this proof go through. That's what I'm going to do. Okay, so what would be the conditions on this thing? Well, I have to have some conditions. So one is if I want my theorem to be true, at least at a type omega, and possibly more, I want this thing to imply that M terminates. Because the way I set my theorem is I tried to, in a way, make it as weak as possible. Okay, so the only thing I really care about, according to the premise of this lecture, is reducible terms of type omega terminate. And I don't necessarily care about reducibility at other types. Okay, so that's a first condition that I need. Okay, and now I need some other condition. And the condition that I need, if you look at this theorem again and just magically replace these by reducible, okay, and in fact, even the jump to reducibility at a type is a bit of a jump, but let me just even omit that for a minute. I want reducible at, I know that M is reducible, N is reducible. Not merely, possibly, that it terminates, but that it's reducible. And so what I want to do is I want to have reducibility be strong enough so that reducibility of M together with reducibility of N together implies the reducibility of Mn. Okay? And what I'm going to do is I'm going to take that as a condition. I'm going to take it as a condition. In fact, it's going to end up being a definition, and now you'll see why the types come in. But I approximately want to say Mn is reducible. Okay, well, if M is reducible, I would certainly want this, and N is reducible, I'm leaving a little space there for a reason, imply that the application is reducible. Okay, this is what I want. Why? Because that's what I needed here. Whatever business goes on in here, like that I was sketching out, the upshot of it should be that the individual reducibility of the two components of the application should suffice for the reducibility of the application. Now, in order for that to make some sense, there's a worry here, okay? Because suppose I try to say this is somehow constitutes a definition of reducibility. Well, it's a problem because it's circular, and not only is it circular, but it has the so-called negative occurrence of the thing you're defining. That is, I say, if this is the case and this is the case, then this is the case, and it's not obvious that such self-referential condition is sensible. But it is. And the reason is I'm going to take advantage of types. So the point is that the reason I have this here is I'm going to stipulate that if M is reducible of type A arrow B, and N is reducible at A, then Mn is reducible at B. And in fact, what I'm going to do is I'm going to actually take this as my definition. So let's make sure this is the condition we need, and then I'm going to tell you what the definition is. Okay, so we're going to need this as my condition. And the reason this is going to be helpful to us is exactly because reducibility at a complex type is explained in terms of reducibility at its constituent types. Okay, this is important. And what I do in my next lecture, or the one after, will threaten this. And that's where a lot of interesting things happen. But for right now, we have this idea that the condition is phrased nicely in terms of constituent types for a complex type. So now here's what I'm going to do. So if this condition holds, and this condition holds, then I'm doing okay. Like at least I've covered the application thing. So now I have to decide like how do I make the whole proof work? And that's where all of the conditions are going to come in. Okay, so of course I now have to revisit these examples because it's no longer obvious, okay, from my definition. I now have to prove, yes, okay, one moment. I would have to prove this, for example. Okay, go ahead. Who had the question? Oh,
Yes, I had a question. So with this formulation, we are not able to prove directly termination as a function type, right?
yeah, so that's why I phrased the theorem the way I did. Okay, but actually I haven't given a definition yet, so you're again a step ahead of me, but yes, what you're saying is totally correct. Okay, but, okay, yes.
So, condition 2, if you have 2 implies, can you emphasize where I actually parse?
Oh, do I? Okay, yeah, so I want to know, you can just write it like that if you want, okay. What I was just writing down is, what information am I going to need to make my proof go through, right? I'm trying to do this organically. Right? There's 2 ways to present something, right? One is just to give it in logical order, and you have no idea where it came from. Or the other is to invent it with you so that you can do it yourself. So I'm hoping that by doing it this way, it's a little cluttered. I have to back up and change things and stuff. Okay, that's the penalty. But the benefit is hopefully you'll be able to do this yourself. So that's the point. Okay, so that's just okay. All right, so I haven't defined anything yet. I was just like writing down some things that I'm going to need to know. So there's some other things I'm going to need to know. For example, why would 0 all by itself, just the constant 0, be reducible at type omega? Well, apparently I'm going to need that as a condition. Okay? All right? Because otherwise, I don't know what to do. So here's what I'm going to do. So what I'm going to do now is to write down a definition that is motivated by what I have here. So the crucial idea now which I said before about the idea of logical relations, is I'm going to associate a relation, this is called reducibility, with a type. So what I'm going to do is I'm going to define a mapping. I'm going to have a definition. Reducibility at A of M, where M is a closed term of type A. Okay, and I'm going to define it like this, and it's going to be defined by induction on the structure of A. And that's the critical point, and in the next lecture or the one after, this will become problematic. But right now, it's not a problem. Okay, so here's what I'm going to do. I'm going to define this by induction on the structure of A. So I have to define, let's just go with reducibility at omega and reducibility at a function type. Let's call it A arrow B. And as a matter of foreshadowing things that Frank is going to talk about, what I'm going to do is I'm going to give what is called a positive interpretation to this type, and I'm going to give what is called a negative interpretation to this type. There is room for variation. Okay, I'll come back to that later, okay? Once again, in the fullness of time, one can motivate every single thing. These things are not arbitrary, but at the moment, it's somewhat arbitrary. I'm choosing this definition to make a proof that I have in mind go through, and you might wonder about the variations, and there are a lot. But let's just go with something, okay? So as a matter of terminology, I'm going to interpret omega positively, and I'm going to interpret function type negatively. So what do I mean by that? Negatively, this is the so-called pragmatist interpretation that Frank, so we can interpret this pragmatically, or you might call it behaviorally. And this was called, I think, the verificationist. Oh boy, what adverb would that be? Verificationistically. Ay, ay, ay. Oh my God, that's terrible. Or structurally, that's a little nicer. That's what is going to happen here, or positive and negative. Okay? Eventually, this leads to a whole story about eagerness and laziness and proof search strategies, and there's a wonderful world here, okay, that I'm just broaching as I discuss it. So I just want you to observe a difference in the way I define them. So what I'm going to do is I'm going to define this to hold if and only if either M reduces to 0 or M reduces to some successor and the predecessor is itself reducible at this type. I'm going to remark on that definition in a moment, okay? But the thing I want you to see about this, first of all, is it's positive in the sense that I demand something about what the thing looks like. It's got to evaluate to a 0 or successor. I can look at that bit pattern and know, okay? Is it 0 or successor? So that's what I mean by structurally or verificationist or positive interpretation of the type. A negative interpretation is what I'm going to use here, because what I'm going to just say, I'm going to use the requirement as the defining condition. If and only if, for every M, which would, N of type A, which would be an argument such that it's reducible at A, we have that the application is reducible at B. And this is so-called negative interpretation. So this is this and this is this. Why is it negative? Well, I don't know why the word negative, but the reason it's negative is because I only care about how the function behaves. I don't care about what the function is. Now, the truth is, in the setting of Gödel's T, I could actually give a positive interpretation of the function space, and I just chose not to for presentational purposes. Okay, that's actually a fact. But here, I'm just, so for illustrative reasons, I'm doing it this way. Okay, so notice that, okay, now there are two questions. Why is this well defined? Let's make sure we know why this is well defined. And so for the two of them, we have two questions here. So for this one and for arrow, let's write omega and arrow just to remind ourselves. Okay, for arrow, it's because it's induction on the structure of A. So, on the structure of the type. the condition for A arrow B is defined only in terms of the condition for A and the condition for B. So in other words, we can think of reducibility A and B as being already done and over with. We're finished with their definition. And now we bump up, elevate, or lift the definition to function types. And we keep doing that. Okay? So for function type, that's not a problem. It uses reducibility only at a constituent type, and so that's good. But what about here? Here it is positively, so to say, circular. The reducibility at omega is defined in terms of reducibility at omega. So what I claim is I'm defining it as a, so to say, a local inductive definition as the strongest such relation. And this will give rise to an induction principle. What do I mean by the strongest such relation? That is, what I'm saying here is that red omega is the strongest P, property P, on closed terms of type omega, such that, well, one of these two conditions. Either, what do I want to say? If m reduces to 0, then P of m. And if m reduces to, and we want to say it either, it evaluates, and either, if it reduces to this, then P of m prime. And m evaluates, you could write it like this, 0 or some successor. Okay? So you want to say it's the strongest one. So in other words, or the least thing, or the intersection of all such things, or however you like to formulate that. I want it to be the strongest predicate satisfying these conditions. Okay? So I claim, and now this is a point about proof theory, and in a way it was kind of hinted at by a question at the end of Frank's lecture, is what makes you think there is such a thing? Okay? Oh, sorry, yes?
What makes one property stronger than another?
Oh, you could say that one implies the other, just like the usual thing. A is stronger than B means A implies B. That's just, so there's a question, okay, sorry.
So from the sort of set theoretical containment perspective, strongest means smallest?
Yes, right, exactly, yeah. So if you interpret a predicate as a set of things that satisfy it, then it's set containment, but that's just another way of saying implication after all. So yeah, so that's just implication. So the question you can, I'm coming toward the end, the question is, you could reasonably ask is, why is there such a strongest P? Well, okay, and then this is more or less the foundational question that was asked earlier. At the end of the day, there's something you have to believe. Okay, and the idea of a strongest predicate closed under some conditions, I think, is a perfectly good starting point. You can paraphrase it in terms of sets and write it out as sets and take the intersection of all the sets that are closed under some operator, and that might appeal to you. That's fine. I don't have any objection to that. But bear in mind, you're accepting a hell of a lot more, okay, by considering that to be a justification than you are by simply saying the strongest P exists and I agree that it exists. Okay? Another way of saying this involves, maybe I should not go there, but in some sense, no, I have a point, but I'm trying to figure out how to say it concisely. You always have to go, if you're doing some meta theory about a system, this is a very approximate statement. It can be made precise. You've got to go beyond the system in order to reason about it. Okay, that can be made precise, but, this is where the rub comes in. You have to accept, it's a comprehension principle, you have to accept that there exists such a predicate. If you don't, nothing I say from now on will make any sense whatsoever. On the other hand, then I would say, I think you're a little crazy. Okay, so.
If you do formulate a set theoretically, do you happen to know what axioms you believe about set theories, ZFCs?
No, it's not extremely strong at all. Yeah, so, no. I don't know what the weakest thing, I have to think about what the weakest thing, but fundamentally it's just a set of natural numbers that is defined by, a closure property. It's a very simple, it's a very simple thing. But in the next lecture or the lecture after that, I'm going to ask you to swallow something much bigger. Okay. And depending on how I present it to you, it will either seem dead obvious, like what are you talking about, or you'll say, there's no way I buy that. Okay, it's going to be one or the other. We'll get to that later, okay? But I just want to say, as a matter of like clarity and foreshadowing what comes later, you've got to accept that this is a valid definition. If you don't, A, I can't talk to you anymore, and B, I really think you ought to. Okay, yeah.
In the most general case of defining this reduction, are so your index across these types, or these classes of types,
My what, sorry?
your index across these classes of types. So you've got
Yes.
reduction omega, reduction over function.
Yeah.
Are they always going to be structured strictly, or is there going to be any mutual
The only question I don't understand is, what do you mean by always?
They're always small.
I mean,
If we were to be doing this for a larger language.
no, so the answer to that is no, and every language is a story unto itself. And the reason I chose the particular three things were they're illustrative of the complications that arise. They're by no means categorically complete or anything like this. It's just, here are some nice nuggets that I'm picking out for you. But basically, everything is its own story. Honestly, there's no like blanket statement to be made.
I have a related question. Is there a logical relationship for dependently typed languages?
Sure.
Okay.
That's my point.
Okay.
I don't know that I'll get there, but
Okay.
that is, I'm hoping to do that in order to give everyone a flavor of what happens when you do this, what happens when you do that, what are the issues. That's what I'm, what's that?
Because then it can get really complicated because we already define it on dependent.
It can get quite complicated, and what I'm hoping to do is to show you that by developing the theory of logical relations, pinpoints what the complication is. Okay? That's another way of saying what I'm doing here. I'm just isolating for you the spots where you have to believe something, or you have to, like, where something seems questionable at least, and everything else will be routine. That's the point. I'm just trying to get it right down to distilling to the one thing in each case, okay, that makes life hard. And that, I hope, will be useful to you. That's my point. Because experience has shown that these are the tools that people use. So the stuff that Amal is going to talk about takes this and puts it on steroids and does like really wonderful things with it. But if you don't have a really good grounding in the real basics, which I'm doing here, then you will have a very hard time understanding the inside game of what she's doing and others are doing. So that's my purpose of trying to do this very organically. Okay, so that sort of brings me pretty close to the end of my time, but let me go a little bit, like maybe five more minutes or so, because I want to get to a decent breaking point. Okay, so we'll get to a certain point with this. So now let's go back, and we want to redo this theorem. So now, let's see, I'm trying to think of like where should I put my finger where there's a soft spot here, okay? So I know where one is. So they're all over the place, but let's just continue here. So this case now I've handled very deftly, by definition, okay? So I've made things work really, because there's another strengthening of the IH that goes on here. That's what I'm trying to get to, okay? So going back now to the original story, we were thinking we're going to prove that closed terms of type A are reducible, and we're going to arrange things. Oh, by the way, notice that by taking the positive, that's what I forgot to say, by taking the positive interpretation here, I've made it blatantly obvious that if M is reducible at omega, it does in fact terminate. I forgot to remark that. So that's part of the positive interpretation. I say positively, that's got to come down to zero successor with a certain condition, okay? So I've arranged this, and I've arranged this because by definition, okay? I just said this is true by definition. Okay, so therefore this part of the proof is easy. So it's immediate that Mn is reducible at type B. Well, we have to fill in our types. And now we're doing this for general types, so let's write this B, B, okay, so we'll take, this is A arrow B, this is A, and then just by definition of reducibility, Mn, and ooh, we're in good shape, so that's great. Okay, so now for symmetry reasons, let's go and look at that was function elim. Let's look at function introduction. We have to look at it again now. So we're still at the moment considering closed terms. We're going to have to change that. Okay, so we do this. So we have this, just to remind ourselves what the rule is. Okay, good. And what do I have to show? Just to remind ourselves, we want to show that the lambda is reducible at A arrow B. Right? Just remember, that's what we're doing, right? Okay, so the theorem has been revised that says closed terms of any type are reducible at that type. So here's an example of a closed term at arrow type, and I want to show it's reducible. So how do I show it's reducible? Let's look at the definition. Well, reducibility is defined this way. So what we do is we say, suppose that, let's call it n, is reducible at A. And what do I have to show is that the application, lambda xam applied to n, is reducible at B. If you don't mind, I'm going to erase over here. Okay? All right, so that's what I have to do. So, well, so far I don't have a lot to work with. And the reason is that I don't have much of an induction hypothesis here. Because unfortunately, so right now I'm kind of stuck, right? If all I know is I want to show that this is reducible at A or B, so I take an argument which is reducible. Okay, that's good. I have to show that this is reducible. So the problem is, right, what do? Well, obviously I want to know something about the body of that function. I want to know something about the behavior of that function. So the point is let's think about what's going to happen here. Well, what do we know? We know, as I remarked earlier, that this has the property of being an executable instruction, and this goes to n for xm. And what we know is, by the way, we have a strong hypothesis now about n, which is that it's reducible. Oh, this should have said reduce, sorry. And this should too. Excuse me for being a little sloppy there. Okay, so this is reducible at type n. So I have an open term. So this suggests that what we do is we prove an even stronger theorem that says, well, if I want to say something about n for xm, which it seems like I probably have to do because reducibility eventually wants to say something about termination, and this is an application, and the way it runs is by doing this step. So it's pretty much inevitable that the n for xm has to be considered. Therefore, I have m, I have to say something about open terms. So the obvious thing to say is this. I'm going to change the theorem to the following. And we'll get rid of that. And we'll say this. So we'll say, in general, for open terms, and let's write it out with the gamma being explicit like this. If this is the case, I want to say something. Now, it doesn't make any sense as matters stand to make a direct statement about m because it's not a closed term. Reducibility is defined only for closed terms. But what I can do is I can say all the closed instances by reducible terms are reducible. That's what I'm going to do. So I'm going to say that reducibility at A1 of M1 and reducibility at Mn imply, those things together imply the reducibility at A of, M1 through Mn substituted in M. This is the theorem that I'm going to prove. Why is that good? Well, the reason is, we're almost done. We're almost there. Because what do I know now by induction hypothesis? If I just look at this case again. So by induction hypothesis, I know that a reducible n for x will give me a reducible instance at type B. So we know, since n is reducible, we know that n for x m is reducible at type B. That comes from the inductive hypothesis, right? Because by induction, I have a typing derivation of an open term. I'm suppressing all of the other variables now in order to focus attention on the crucial thing. So I'm going to have some other variables in play. Let's leave those aside for right now. And I'm saying, for this to be well-typed means that you have an open term with this variable. Something with a variable is interpreted as a function that takes reducible arguments to reducible results. Here's my reducible argument. Let's plug it in. So what do I need to conclude? What I have is this. What I want is this. And the step is, what happens is I need to know that this reduces to that. So what I need is a lemma, which is called head expansion. Or if you want to sound perverse, you can call it closure under reverse execution, which is exactly what it is, except you would think, why on earth is reverse execution relevant? Well, here's why. So what you do is you say, if m takes a step to n, and n is reducible at some type A, this is for every A, then m is reducible at the same type. Clearly, that lemma suffices for this step. So the result follows by head expansion. And then we're done with that particular case. But I need to prove head expansion. So as I say, when stated in absolute isolation, I don't know, at least to me, it struck me as like just completely bizarre. Why would it be important to run something backward? Okay, it's kind of crazy. It seems crazy, but the reason is it just comes right out of the proof. We have to show that this is reducible, and this thing runs to here, and that's known to be reducible by induction once I strengthen the induction hypothesis now twice. Twice, right? One is to prove a stronger property called reducibility. The other is to consider open terms. Okay, so I do that. Okay, so now this is my lemma. And how do I prove closure under head expansion? Anyone have an idea of how we might do this? And this will finish us, Christina, on
Induction on type.
A. Yeah. So we can do this by induction on A. So induction on the structure of A is what I would do here, right? So one possibility is A is omega, and then I'll finish. The other is it's A1 arrow A2. And now what I want to show you is a bit of an inner game here. Everything I've done is defined to make this be true. Okay, and this is where the back and forth comes in. So when you set up the language, certain things are kind of forced on you for reasons that only become apparent like here, and I'll show you where. Okay, so let's look at omega. This is obvious because it's given by a behavioral structural condition. Because what I do is I say, look, we assume that n is reducible at omega. That means it reduces either to 0 or successor. But if something reduces to it, which reduces to 0, then the something reduces to 0. Or it reduces to it, which reduces to successor, means the something reduces to successor. So this is immediate from the definition. Because, as I say, because we know that either n reduces to 0 or n reduces to successor of n prime with n prime being reducible. Sorry. And we know that m reduces to n, well, in fact, by one step, okay? So therefore, it reduces either to 0 or to the successor with the thing being reducible. Okay? So it's completely immediate. So it's part of defining it behaviorally or structurally. It's immediately closed under head expansion. What about A1 arrow A2? Okay, so what do we know here? So let's write it down. So we assume, just to be explicit about it, so now we're looking at a function. So A1 arrow A2 of n, all right? And we want to show, and we know that m reduces to n, and we want to show that m has this property. Well, how do we do that? Well, we say, suppose we have an argument. Let me just call it R. I'm sorry, reducible, red, excuse me for doing that. So if reducible at A1, let's call it M1. And what do I want to show? Reducible at A2, of course, of M applied to M1. So here's the crucial thing. This is a smaller type. And here's what we know, is we know that since M steps to N, that implies that M applied to, what did I call it, M1, steps to N applied to M1. Therefore, by induction, that is, the head expansion at A2, I get that N applied to M1 is reducible at A2, and that's what I need. okay? Or M, I've got my M's and N's backward, okay? But it follows, oh, right, because we know that this is the case, so let me write it out. let me write it right here. So under the assumptions we have is we know that reducibility at A2 of N applied to M1. Why? Because M1 is chosen to be reducible at A1, and N is assumed to be reducible, so its application is reducible at A2. And then by this principle of evaluation, which says that you can evaluate the function position, you can evaluate an application by evaluating a function position, then I know by induction, because it's a smaller type A2, by induction, we know that reducible at this smaller type, MM1, and that's what I needed, because I was trying to show that M is reducible by applying it to a reducible argument. And that's it. So my point is that this rule here, which I wrote something like this, is crucial. Okay? And these two things work together. Okay? The idea that I had that rule, I motivated it by, you know, if you want to evaluate these things, this is what you have to do, and it seemed plausible. And anyway, it's a definition, so I can define it any way I want. But the reason, the inside game of why I defined it, is because I need to make this lemma come true. Okay? And so this instruction step has to be there in order to make the head expansion lemma come true, which is necessary for this main theorem, which I haven't finished proving, and I'll do next time, to come true. And so that's what I was showing you. So I'm going to stop there. Okay? So the moral is, right, so far, is we came up with this idea of associating a predicate, reducibility predicate as it's called, with a type, using some principles of definition that I hope you would accept. And given those, we proved a strengthening of the original theorem, which implies the theorem we wanted, that says an open term is if it's well-typed, is reducible at M, but not just that, but all of its instances by reducible terms are reducible. And then as a corollary, we get the theorem that we want. Okay, so that's the plan. So what I'm going to do next time is actually do that proof, because the case for the recursor is interesting. And then I'm going to do this with binary relations to give you a way of reasoning about equality, okay, of these terms. So that's what I'm going to do next, and that's in the PFPL book. Then I'm going to amp it up to polymorphism and talk about the theory of equality for polymorphism, which is the theory of parametricity. And then that's what I'll do, and I'll prove some representation independence results, crucial ideas about abstract types, and that's a kind of foundation for some of the other lectures. And then I hope I'll say something about dependent types. Okay, so that's the plan. Okay, thanks for your attention.
Okay, so if you owe me money, you should bring it after lunch. If you're going to pay me by check. If you want to do laundry, I have a laundry card. You should buy